Hello everyone, Mr.Waz here and welcome to WasleyScience. Today we're going to be talking about energy. Now I'm going to be going a little fast when we talk about kinetic and potential energy. We're also going to be talking about the two energy formulas, and we're going to be talking about the 5 forms of energy as well as energy transformation. Now again, this is a little bit of a review for you guys, so if you are not familiar with these terms, feel free to press pause and do whatever you need to do and go at any pace that you need to go. Alright, so let's get started. Here's some 3 words, basic vocab words for this unit. First is work. Now work involves moving an object a certain distance. If you are just lifting a box from the ground 1 meter high, that counts as work. But if you have an example of somebody just holding an object in the same place, that doesn't count as work, because for work to happen, the object needs to be moved some sort of distance. Work is measured in newtons. And then we have energy. In order for you to do work, you have to have energy. It works like the currency. Energy is usually measured in joules as well as calories. And then power is the rate of doing the work. So power involves time. So power involves the time in which you are exerting the work and using the energy to exert the work. We're going to talk more about power when we get into the electricity unit. Alright, so let's focus in on energy here. There are 2 types of energy, kinetic energy and potential energy. Potential energy is the stored energy, and kinetic energy is the energy in motion. I'm sure that you've heard this before. Here's some easy graphics to understand this. So when you're at the very tippity top of a roller coaster and you're about to fall, that's when you have the highest gravitational potential energy. And when you are at the bottom of the roller coaster, like right here, and you're in motion, that's when you actually have the highest kinetic energy. So as you go up, your kinetic energy will begin to drop and your potential energy will begin to rise. And when you get to the top, your potential energy is at its highest, and then the kinetic energy is at its lowest, and then as you're going back down, getting faster and faster, your kinetic energy rises and your potential energy drops. So they're interchangeable. You can't have really high potential energy and really high kinetic energy at the same time. You can't have one and the other, in other words. Now on to the formulas. So the formula for gravitational potential energy, also known as GPE, is really easy. It's just mass times height. In other words, the more mass an object is, the more potential energy it could have. The higher that object is, the more potential energy it could have. So if you just have a baseball at the end of your desk, it has potential energy, but not nearly as much as a piano on top of a skyscraper. The formula for kinetic energy is a little bit more complicated. It involves mass, just like potential energy does. So the more mass something has, the more kinetic energy it could have. But this one involves speed or velocity. So the faster the object is going, the more kinetic energy it has, which makes sense. So in order for you to use the formula, you have to actually multiply your speed by itself. And then for the mass, you need to take half of the mass. And then once you've had half of the mass and you've multiplied the speed by itself or squared it, then you can multiply them together and you will have your kinetic energy, KE. We're going to be practicing this in class, so if you're feeling overwhelmed right now, don't worry, just get down the formulas and you'll be fine. Hey guys, why don't you take a short break right now and click on the video to watch an MIT professor who shows you the properties of physics and plays around with a pendulum. Really cool. He eventually will put it up to his face and let it go and see if it hits him in the face. Hopefully the laws of conservation of mass will kick in for him. But yeah, I really like this video. I wish I could do it in class, but I don't really have the space. Alright, let's do our own example of energy conservation. So I have this rhino on top of a building. It has a lot of potential energy because it's a rhino and it's on top of a building. And remember that the formula for gravitational potential energy is mass times height. So yeah, this guy's got a lot of gravitational potential energy. Let's see what he does. Oh man. Don't do it. Oh god. Oh. Okay. Alright, so he jumped. Now, during the fall, his potential energy is dropping and his kinetic energy is rising. It's being converted from potential energy to kinetic energy. And a small amount of it is being transferred into heat. As the rhino is moving through the air, he's crashing into molecules that are in the air and producing friction. So he's going, he's going, he's going. He's going, he's gonna, oh my gosh, he's getting wet. Oh! Oh! Ooh. Yikes. Alright, so, yeah, he just hit the ground. I hope he's alright. So upon impact, the kinetic energy was transferred into a bunch of things. It was transferred into heat, it was transferred into sound, and then there was energy that was put into the pavement, which caused chemical bonds within the concrete to break. So yeah, his energy now is no longer really kinetic energy. He's back to just having, oh, he's alright, thank goodness. He's back to having just potential energy. And overall, through this whole situation, the total energy remained constant. That's the real point of this whole animation, guys, is that the total amount of energy remained constant. Your potential energy could drop and then your kinetic energy will rise, or vice versa. Okay, so that's really important, is that we never really lose energy. We don't create energy. We don't destroy energy. You cannot create or destroy energy. It can only be transferred from one thing to another. Hey guys, if you want to watch a terrible video on energy and kinetic and potential energy, feel free to click on the link right here. You can torture your friends. Enjoy. Oh my gosh. Alright, now we're going to move on to 6 forms of energy. So before we talked about 2 types of energy, which is kinetic and potential. Now we're going to talk about forms of energy. So we're going to talk about mechanical energy, thermal energy, electrical energy, chemical energy, nuclear energy, and electromagnetic energy. So our first form of energy is mechanical energy, and that's really the energy that's associated with the motion or position of an object. It's when work is being done, you're using mechanical energy. So it involves potential energy and kinetic energy. So it really goes hand in hand with our 2 types of energy that we've been talking about. Our second energy is thermal energy, and thermal energy is released when molecules collide, and the higher the temperature, the more the molecules collide, the more thermal energy that gets released. So that makes a lot of sense. The colder the temperature is, the less the molecules are going to bump into each other, so there's going to be less heat. Our third form of energy is electrical energy, and we're going to be talking about this a lot more in detail in Unit 3 when we get into electricity. But what you need to know now is that electrical energy involves the movement of electrons. It specifically involves the electrons. Hence why the name electricity, because electricity involves electrons. Okay? So whenever there are movement of electrons, there's electrical energy that is formed there. Then we have chemical energy. And chemical energy is a type of potential energy, and it's energy that is stored inside the chemical bond. So all food that we eat has chemical energy, some more than others. So let's talk about a quick energy transformation here. Let's say you eat some food and your body will begin to digest the food and break down those large molecules in the food into smaller molecules, and then at that point respiration will take place, and during respiration the energy from the food, those molecules, those chemical bonds, get converted into thermal energy, heat, and that heats up your body. And at that point you can use that heat from your body to then use mechanical energy to move around and eat some more. And then that is how we are able to sustain life. Alright guys, let's keep the ball rolling here. And by ball I mean the sun. Our fourth energy is nuclear energy. And I'm going to talk about an example of nuclear energy, which is fusion. And fusion occurs in the sun. Now, it doesn't occur on the outside of the sun because fusion requires extremely high temperatures and pressure. The outside of the sun's only like 6,000 degrees Celsius. Not really that hot. But the core of the sun is over 1,000,000 degrees. That's where you have hydrogen atoms, you know, the most simple elements, just one proton, one electron, combining together to make helium. And that process is an example of nuclear energy. So fusion is just one example of nuclear energy, but another example of nuclear energy is fission. And fission is the opposite. So rather than two atoms combining together, fission is when you take one atom and split it apart. And that's what happens with nuclear power and on nuclear bombs. So if you just take a uranium element and you use a single neutron to split it in half, like in this picture on the right here, it will cause a chain reaction within the fuel rod in a nuclear power plant, and that chain reaction will release massive amounts of energy, just massive amounts of energy, beyond your belief. So a typical pellet of uranium looks like this picture here. That's just one pellet. It's about 7 grams. It could generate as much energy as 3.5 barrels of oil. And just to give you perspective, a barrel of oil is around 50-ish gallons, or 17,000 cubic feet of natural gas, and 1,700 pounds of coal. So nuclear energy by far can get you the most energy. Now guys, don't get me wrong, nuclear power comes with a price, and the price for nuclear power is that when a fuel rod is all done, it is then releasing very harmful radiation, which you may be familiar with. And we have to do something with these fuel rods. Right now, our best idea is to bury them in a mountain in Nevada called the Yucca Mountain. So that's what this picture here on the bottom right is. So with every great thing comes a price. Alright, so let's move on to the last form of energy we're going to talk about. There is a 7th energy, which is sound energy. We're not going to get into that though because it's not really necessary for our curriculum. You can save that for when you take physics senior year. Now, electromagnetic energy is the energy that can travel in waves through space. No direct contact is needed with the energy. It comes in many different forms. Gamma rays, which is a harmful radiation that gets released from fuel rods after they're used. There's ultraviolet rays, also known as UV rays. That's the radiation that the sun releases that could give you skin cancer if you don't have sunscreen. And there's also infrared rays, radio waves, X-rays, visible light rays, and microwaves. So we should take a moment right now to really be thankful for the sun, because most of the energy that we have here on Earth came from the sun in one way or another and then transferred to other energies. The only energies that really didn't come from the sun is the energy that is within our Earth, the core of the Earth, which is a geothermal energy, but that wouldn't really help us create life. The only other energy that I can think of is the gravitational pull of the moon that creates our tides, but again, that's nothing that can really help us with life. So all of the energy that we have here on Earth, just about all of it, came from the sun in one way or another. So thank you, sun. Thank you so much. Alrighty then, so we're going to talk about one more thing today, and that's energy transformation, which is a change from one form of energy to another. And we already talked about it a little bit when we were talking about chemical energy. So energy transformation, it really involves with the law of conservation of energy, which is that energy cannot be created or destroyed. It can only transfer from one form into another. And when that happens, no energy is destroyed in the process. So you may be familiar with that law. If you're not, that's a really important concept. It even is called the first law of thermodynamics. It's really the same thing. It's just that energy cannot be created or destroyed. It can change from one to another. And what's really important is the total amount of energy during that time has remained the same. So in other words, I think it's 11.7 billion years ago when the Big Bang occurred, all the energy that has ever existed was made at that point and has remained the same since then. So that's a total mind-blown moment for you. When we talk about energy transformation, we really need to mention friction. I know friction's something you mentioned last year, but let's bring it up again. So whenever an object is moving, it experiences friction. And friction is when an object is moving and it's crashing into molecules in the air, and that's causing thermal energy or heat to be transferred. So when that rhino jumped off the building, the reason it was turning red was that animation was showing that it was experiencing thermal energy, because as it was falling, it was crashing into more and more molecules. And this happens in the atmosphere every day when meteorites or meteors hit the atmosphere. It's because the meteors are crashing into all the molecules within our mesosphere and causing it to break up and experience heat until it's too small to even get to the surface. And another example is if you take your two hands right now and you rub them together, your hands should feel really, really warm. That's friction. That's thermal energy. So you just transferred mechanical energy into thermal energy. So I know it seems we're going all over the place, but we really need to talk about fossil fuels briefly. So fossil fuels are what we use currently to really power our whole world. The three main fossil fuels, oil, natural gas, and coal, they come from plants and animals, mostly plants, that were buried in mud and sand 10,000 years ago. And through heat and pressure, that chemical energy that those plants and animals had become stored. And we're able to extract that energy that's been stored within it by burning it. And by burning it, we can use that energy for electricity. So, maybe now you're wondering, how does energy get to your house? So what I'd like you to do right now is number your paper 1 through 8 and make a sort of table. And after you've numbered your paper 1 through 8, I'd like you to either draw each of these things or describe them if you're not really good at drawing. So take some time right now to do that. And what I want you to do after you've done all that is each picture it's a whole energy transformation process that shows how we get energy to our house. So I want you to write what form of energy, being thermal energy, mechanical energy, chemical energy, electrical energy, electromagnetic energy. Did I say them all? I think I did. Try to label which one is which. Now, some of them have more than one going on, and then there may be a situation when the same one goes from one step to another, but just a different sort of process is happening. So at this point, you can use this as a sort of answer sheet here. You can see in step 1 the sun transfers nuclear energy, which we talked about, which was fusion, into electromagnetic energy to the Earth, which was radiation and UV radiation. At that point, ancient plants from tens of thousands of years ago, they photosynthesize, they use the radiation, and they can turn that electromagnetic energy into chemical energy. And then those plants and animals in that swampy areas, they die and decay. The plants get buried over time, more sediment grows on top of them and compresses them, and eventually they become either coal, oil, or natural gas. In our fourth step here, we have us. That's a picture of a coal mine. Maybe that's the one that people usually have the most trouble with. So with the coal mine, we're able to dig up all those fossil fuels and then carry that chemical energy, the coal, to a power plant, which is step 5. So in step 5, the fossil fuel is burned, and the chemical energy then gets transferred into thermal energy, heat. So that heat then in step 6 is all that heat is placed under a steam turbine, so the heat will rise and the steam will cause the turbine to spin very, very fast. And then so that energy is thermal energy into mechanical energy. And then that mechanical energy, the steam turbine, is hooked up to a generator. And a generator transfers moving mechanical energy into electrical energy. And at last, through power lines and such, the electrical energy can be transferred to your house to use for whatever you desire. So that's a prime example there of energy transformation. We're going to be going to this example a couple times in the year because it's very important for earth science and environmental science. So make sure you're very familiar with this 8-step process. It really helps to draw it out. Credits for some material and organization of this presentation goes to Nancy Salvatore and John Schwartz, and the flying rhino animation comes from Harvard University. Alright guys, that's all I have for you today, so thank you very much for watching. Please remember to subscribe. If you click on the bottom here, you can subscribe to my channel, WasleyScience. And if you need some review, you could click on the video up here, which is a crash course chemistry video. I really enjoy this YouTube channel. I use it all the time in class because they have really great animations. He talks fast and better than me, so feel free to click on it to help you review. Alright, thanks again guys. Take care.